Hey guys, Mr. King here. Today we're going to be talking about waves, and we're going to talk about how waves help to move the ocean water. Now, last time we talked about the different types of currents we have, which help to move the water in different directions. Today we're going to talk more about kind of the up and down of the water rather than just the steady flow. We're going to talk about waves and how they're created, and we're also going to talk about tides and how we have high tide and low tide, and we have these things called spring tides and neap tides, and we're going to talk about how all of that moves around that ocean water that we've been talking about. So first off, we got waves. You guys have all seen waves. We've been down to Lake Michigan to check that out. Waves are formed by wind. A wave is basically a rhythmic movement that carries energy through the water. And there are three things that impact wave height. Number one, speed of the wind. So obviously if it's blowing faster, it creates a bigger wave. Number two, the length of the time the wind blows. So if it blows for a short period of time, you're going to have a pretty small wave. If you have a really fast wind that blows for a long period of time, you're going to get a really big wave. And then number three, the distance over which the wind blows. So once again, if you have it blowing over a pretty small area, it's going to create pretty small waves. But if you have it blowing over this huge space, you get these huge waves. So in order to create the biggest wave, you want a really fast wind blowing for a long time over this huge area. And I've got this video for you, and this is a guy setting the world record for surfing on the biggest wave. Okay, so check this out. Check this out. This is crazy. So that is the world record for the largest wave ever being surfed. And you can see in that case, that wave was created from a really strong wind blowing for a long time, and it's huge. It's blowing over a huge amount of the ocean. And so obviously you put all three factors together, you get a huge wave. So waves, if we want to break them down and analyze them, they've got some parts, they've got some technical names. Crest is the top of the wave. Trough is the low point, the bottom of the wave. The vertical distance, if you were to measure the distance between the crest and the trough, that's known as its height. Obviously, if you're measuring from the top to the bottom, that would give you height. And then the last one's wavelength. And wavelength is the horizontal distance between crest and trough. So if you measured from the top of one wave to the top of the next wave, that would give you the wavelength. Or if you measured from the bottom of one wave to the bottom of the next wave, that would also give you the wavelength. So here's a diagram. You can kind of see it a little bit clearer here. Once again, crest is the top, trough is the bottom, wave height, bottom to the top or from the trough to the crest. And then your wavelength, you can either measure from the top of two waves, or you could also measure from the bottom of the two waves, and those would give you the wavelength. Okay, so those are our technical words. You guys obviously have seen tops and bottoms of waves, and you've probably all played out in Lake Michigan and been smashed by them. But those are the technical terms. So wave motion, this is kind of a difficult one to understand. We'll do a simulation in class where you guys can kind of check this out. Water particles do not move forward unless water is breaking on shore. So if you were down at Lake Michigan and you took a tennis ball and threw it out 50 yards, that ball would bounce kind of in place. It would move up and down as the water goes, but it wouldn't come closer towards you, because the water doesn't actually move in towards the shore. It goes up and down. Now if you get close enough to shore, we get what's called breakers, or you get like whitecaps, and that's where the bottom of the wave starts to slow down a little bit because it's hitting with the bottom of the ocean floor, and then it makes it topple over and you get that whitecap look. So that would be a time where if you threw the ball out like 5 feet it would come in towards you because of the distance between the bottom of the wave and the ocean floor is so small that it's going to make the top of the wave break over and push it in. But if you just throw it out far enough where it's not too shallow, it's just going to kind of bounce in place. And that's kind of a confusing thing for most people because they think, oh, you see that wave, oh, here it comes, here it comes. That wave does not actually come itself. What happens is it transfers that energy, kind of like what we've talked about with conduction, where the molecules bump into each other and transfer their energy. It's the same thing with a wave. It bumps into the next wave and it carries on that energy, almost like a domino effect. So breakers are these things, they're the collapsing waves near the shore. And once again, if you can imagine, the wave is just zooming along, but all of a sudden the bottom of the wave, where the water's moving, starts to run into the sand on the bottom of the ocean floor. That slows it down. So if the bottom starts to slow down, that means the top is still going the same speed. And if you have a top going faster than a bottom, that's going to cause it to tumble over. It's like if you had someone come up and grab onto your feet and push you in the back, your top would go faster than your bottom and you'd fall on your face. The same thing happens with a wave. If you slow it down on the bottom, the top's going to crash. And that's where you get that whitecap look that we see. And that depends on the amount of speed from the wind and the duration, like we talked about earlier with what causes the waves. But it also has to be a spot where the bottom is going slower. So a lot of times you'll see whitecaps not right out on shore, but you'll see them farther out in a lake. And that's because there's a sandbar where there's part of the lake or the ocean floor is built up a little bit more. And that's why you get those whitecaps breaking. So another thing that causes our sea levels to move is tides. And tides are the rising and falling of sea level, and it's caused from the gravity or the gravitational pull between the Earth, the Moon, and the Sun. And you guys know that with gravity, what happens is you have larger objects and smaller objects kind of pulling on each other. And so we get two types of tides. We get these things called spring tides, and it's where the high tides are really high. And since the high tides are really high, that means the low tides have to be lower because there's only a certain amount of water on the Earth. And so if you have these high tides that are extremely high or the water is really far up on the beach, that means when it's a low tide, there's going to be less of it left over to go back. And so that happens when the Earth, the Moon, and the Sun all line up in a straight angle. And what happens there is we have them pulling on each other kind of together. And so when they work together, they make these really high tides and they make these really low tides. Now neap tides are a little bit different. Neap tides are kind of like, it makes it more average. And the high tides are lower, so they come back more towards like normal or average. And the low tides are higher, so they get more towards average. And that's because the Earth, Moon, and Sun form a right angle. Okay, that's like a 90-degree angle where the Moon is pulling the Earth in one direction and the Sun is pulling the Earth in another direction. Now obviously our Moon is a lot smaller than the Sun, but the Moon is also a lot closer than the Sun. And so when you factor in those two things, even though it's small, it's close, so it still pulls on the Earth. Even though the Sun is huge, it's a long way away, so it pulls on the Earth too. And so when you get them not working together, they kind of pull the Earth in two opposite directions, and it makes everything kind of balance out. So here's a picture of a spring tide and a neap tide. And you can see, once again, a spring tide, you've got them kind of lined up working together. And this happens when we have a new moon and a full moon. And we've talked about how the Earth rotates. So as we spin around, we also have our moon going in a revolution around the Earth. And so it ends up in different spots 4 times a day. And so if you can imagine, and you can see on this picture, the moon ends up in 4 different spots. One time it's on the right, one time it's above, one time to the left, and one time down below. And what happens is, in a 24-hour period, you're going to have 2 periods of high tides, and you can see that's kind of where in the top, where the spring, where they're all working together, and you're going to have 2 periods of low tides, which would be like our neap tides, where they're working against each other. And so if we went to Lake Michigan, if we could take a class field trip down to Lake Michigan, and let's say we went down there at 6 a.m. We got to school real early. We walked down there and we marked the water line. We marked where it was coming up on the sand. If we marked it 6 hours later, we would have a significant change in tides. Okay, so that would be at noon. And then in 6 hours later, at 6 p.m., it would be back to where it started at 6 a.m. And then if we finished up the field trip at midnight, we were rocking it out, it would be back to where it was at noon. And so each day you have 2 periods of high tide and 2 periods of low tide. Now this will show you it a little bit better. This kind of shows it all in action. You can see the Earth is rotating, and then you can see the revolution of the moon, and you can see it says neap tide, spring tide, neap tide, spring tide, and that occurs many different times as we spin and as the moon revolves. It's all pulling the water in different directions. Okay, and it's pulling the Earth in different directions, making our water bulge out on other sides. The last thing that happens when we have the water moving with these waves is it crashes into beaches, and it hits over and over again, and every time it hits, it pulls away a little bit of rock or sand or sediment of some sort, and it wears away rocky shores, and this is called wave erosion. And you can see in the picture here, this was probably a straight cliff at one point, but now if you look at the bottom of it, that's where the waves have crashed over and over and over again, and it's actually looks like it's taken a chunk out of the rock. And that's happened over a long period of time, but if you get strong enough waves for a long enough period of time, it's going to keep on eating away at that, and eventually there's not going to be a base anymore for that cliff, and that's going to tumble over into the ocean. And that's a natural process that happens because waves continually are moving onto shore and crashing against different beaches or different rocks, and that erosion happens daily, many times. Alright guys, hope this all makes sense. Once again, as usual, we'll talk about it a little bit more in class, do some stuff with it to help you understand. You guys have a wonderful night. I'll see you all tomorrow.